This is chapter 9.5, solving trigonometric equations. We are on page 6 of the notes. And so now we're going to move on to something a little different. We want to solve these trigonometric equations using the identities we looked at last week. Okay. Problem is that these typically aren't set up so that it's super obvious which identity we want to use unless you're really familiar with them. So it's helpful as you go through these, if you have a page with your identities on it, keep them right next to you. Sometimes it takes a little bit of time to figure out which we want to use. Okay, so we want to use the identities here to solve exactly on this interval. We're on the unit circle again. We've got cosine x, cosine 2x, plus sine x, sine 2x equals square root of 3 over 2. Not loving the fact that I've got both cosines and sines, and I've got two different arguments. I've got x and I've got 2x. And those are two totally different numbers. So I'm going to start by thinking of this way. Cosine alpha, cosine beta, plus sine alpha, sine beta. I've just replaced my x and 2x with alpha and beta. That is the difference of cosines. That's cosine alpha minus beta, which means I can rewrite the left-hand side of the equation as cosine x minus 2x. Right side of the equation stays the same. I've got square root of 3 over 2. That gives me cosine of negative x equals square root of 3 over 2. I know that I can use that negative angle identity. Cosine is an even function, so cosine of negative x is the same as the cosine of x. So I got cosine of x equals square root of 3 over 2. And so now I'm at the point where I got to figure out where x, the cosine, what x has to be so that the cosine is square root of 3 over 2. We know that cosine is positive in quadrant 1 and quadrant 4. Square root of 3 over 2s are my pi over 6s, so I know that x is pi over 6. There's my quadrant 1 value. Or 11 pi over 6. There's my quadrant 4 value. I'm going back up to my problem statement. I want to solve this on the unit circle, the interval 0 to 2 pi. So that is it. X equals either pi over 6 or 11 pi over 6. And that one's done. Exercise example 14, solve the equation using a double angle formula. I got cosine 2 theta equals cosine theta. So let's talk about our double angle formula for cosine theta here. Cosine 2 theta. If you remember, this one had multiple possibilities. So I could use cosine squared theta minus sine squared theta. If I use that to replace the left-hand side, now I'm introducing a sine squared theta. I don't think I want to do that. I also could use 1 minus 2 sine squared theta. That does not seem to be any more useful than that first version. I still don't want to mix cosines and sines if I can avoid it. Or I have 2 cosine squared theta minus 1. And I think that's going to be the way to go because at least I keep everything in terms of cosine thetas. So I'm going to go ahead and use this to replace my left-hand side. So let me rewrite that here so we can follow. We've got cosine 2 theta equals cosine theta. I can rewrite that cosine 2 theta as 2 cosine squared theta minus 1. Now this is starting to look a little more quadratic. I want to get everything on the same side, so I'm going to subtract cosine theta from both sides. I get 2 cosine squared theta. I'm going to write it in descending order, so minus cosine theta minus 1. And now I'm going to factor. I could substitute in with an x, but given that I just have a 1 here, think I should be okay. I need a negative cosine theta in the middle, which means my 2 cosine theta's got to be negative. My 1 cosine theta has to be positive. I got 2 cosine theta plus 1 equals 0. So I'm looking for where cosine theta is negative 1/2. I get cosine theta equals 1. And so let's take a look at what we got here. Cosine theta is negative 1/2. Let's see, that puts cosine in either the second or the third quadrant. That is true at 2 pi over 3, 4 pi over 3. Cosine theta equals 1 at pi. I'm going back up. No, it doesn't, at 0. Cosine theta equals 1 at 0. Ignore that. I'm going back up to look at my problem statement. It just says solve the equation using a double angle formula. This is not limiting me to the unit circle. So this time my theta looks like 2 pi over 3 plus 2k pi, 4 pi over 3 plus 2k pi, or 0 plus 2k pi, which we really could write just as 2k pi, and we need in here that k is an integer. And let me separate this because I'm infringing on that bottom space just a little bit. Started writing really big. Okay. Last one, I got 3 cosine theta plus 3 equals 2 sine squared theta. And we saw one of these in the last couple of pages. I really don't want to work with both cosine and sine, given that my sine is squared, so I can rewrite that using the Pythagorean identity. I get 3 cosine theta plus 3 equals 2 times 1 minus cosine squared theta. I'm going to move everything to the left-hand side and multiply that 2 through. So I get 2 cosine squared theta plus 3 cosine theta plus 3 minus 2, so plus 1. We're going to factor this. We got 2 cosine theta times cosine theta. Only way to get 1 is 1 times 1. I want a positive 3. These are both positive. I'm going to solve for cosine theta here. I get cosine theta equals negative 1/2. Cosine theta equals negative 1. Cosine theta is negative 1/2 at theta equals, same as above, 2 pi over 3, 4 pi over 3. And my other theta here, cosine theta, is negative 1 at pi. Notice here, we just want solutions on our unit circle between 0 and 2 pi. And so this is it. We don't have to worry about anything coterminal to these three.